Welcome to the Beneski Museum of Natural History at Amherst College. We're about to take a tour with Dr. Stan Rachootin of Mount Holyoke College. Stan began working at Mount Holyoke in 1984 and over decades has taught numerous classes on Darwin's work. Today he's going to take us on a tour of some of the key elements of the Beneski collection.
So, note, by the way, there are spectacular specimens in all of these drawers, smaller specimens that you can pull out. Those of you who are taking the class pass-fail don't have to worry about these drawers, but otherwise, before you take the test, you should do all, no, just a joke. Okay, quick little account of vertebrate evolution. I mentioned talking very briefly about fish. The fish don't have hands, and so if they're going to have a better control of their world, they're going to have to open their mouth and gape wider. This is the first fish to have a jaw. And this is a placoderm, and this is a genus called Dunkleosteus from Ohio. And up here, it can tip its whole skull up into that space while dropping its lower jaw and take a really big bite out of something, using that sharp stuff in front, which look like teeth, but they haven't figured out teeth yet, so those are made out of bone. First fish with a functional jaw. This is a relative of Dimetrodon, the sailback proto-mammal, which used to be called a mammal-like reptile, but here's Edaphorus, which is a smaller version, and many different sizes of sailbacks. They're all Permian and basically Permian, before the Permo-Triassic crisis. And because we have a bunch of different sizes, we know that the surface area of the sail always fits remarkably well with the mass of the body underneath. And so before we figured out on the mammal line how to warm ourselves just using chemical things in our body, you could turn your sail to the sun and warm yourself up. And when you're warm enough, just make sure you're not facing the sun with that whole big surface area. The one I really want to talk about here, however, is Archaeops. Archaeops is about 25 or 30 million years after the tetrapods came out on land. And one of the reasons we can tell that is that we have 5 fingers on the forelegs and 5 fingers on the hind legs. When they started out on land, they had all sorts of numbers. The numbers were never 5. They had 4 and 3 on the side, or just 4, but no, it took them about 25 million years to say, hey, let's do 5, and let's do them forelimb and hind limb. They would have different numbers on the forelimb and different numbers on the hind limb. At this point, this is an animal that's living its adult life on land. But the first things to work out, being tetrapods, being amphibians, lived their whole life in the water. They had gills all the time. They had a lateral line system for feeling water motion, which does not work out of the water. By the time you get to Archaeops, you have a neck. Because if you've ever watched a fish in an aquarium, if a fish wants to look at something or eat something, the fish turns like that. It doesn't have a neck, it doesn't move its head back and forth. Necks didn't evolve till we came out of water and discovered, oh my goodness, this head is really heavy. Or this body is really heavy, I'm just going to move my head. Until that, the neck just went, there was no flexible neck that you could use for moving, just your head to see what's over there or take a bite out of something without moving your whole body towards it. In the water, you're weightless because your body is basically water and it's surrounded by water. The other thing which is really neat is that in the beginning, when we first came out of water and started breathing air, there was, of course, no diaphragm. There's no diaphragm until you're a mammal. Birds don't have diaphragms. Reptiles don't have diaphragms. How could an animal this big, and the first things to come out of water were about this big. They were big carnivorous things. the only way they could get out of the water and get air, which from their now very heavy body, which is crushing down on their lungs, which is not a good way to get air to your lungs, is to prop themselves up on their forelegs and gulp air into their gill chambers, which are actually what lungs are that don't open to the outside. So a gill opening that doesn't open to the outside, you call that a lung. Your lungs are gills but gills are supported by water, so the filaments can float. In air, they don't float, so we stick the filaments, or the capillaries, between little sheets of very, very thin tissue. And that's what keeps your lungs from collapsing on themselves and all of your respiratory tissue from collapsing on itself. Meanwhile, the hind legs were generally, in the very first tetrapods, very small, and they just kept your rear end from slithering too much to the left or right. You could just brace yourself with them. So the front end, your front limbs were part of your breathing system, and your rear legs were just trying to keep control of your rear end a little bit. Once you start walking with your forelimbs and your hind limbs together, then we start to get a reason for development to work the same way on forelimbs and hind limbs. And what example do we have? And what example do we have in class of something that changes on the forelimb and then comes through and changes on the hind limb also? Actually, we had a bunch of these things. Fusions in the forelimb and hind limb of frogs, which makes sense for the hind limb, but not for the forelimb. All those fusions in the wing of a bird, and then the same fusions show up in the feet, even though it doesn't make any sense in our feet probably work better than a bird's foot, where you're just hopping around. But, they fused up their forewings, they fused up their hind legs too. Their wings, that is. And the panda's thumb, where you get something like this in the forelimb, but you get the same sort of thing in your hind limb, and you don't do anything with it, and you can't do anything with it, but hey, it plays out doing the limb things. Okay? So, could we say that because development evolves, you could get more homologous over time if you start using things like forelimbs and hind limbs together? They become more similar developmentally, and then they're more homologous 25 million years after you first start getting them than they were at their first appearance. It makes sense if development is part of your notion of what we mean by homology, but if your notion of homology is strictly, it is a synapomorphy. The synapomorphy is there from the beginning, and you can't get more synapomorphous than that. So a cladist goes crazy when somebody tries to tell a cladist, gee, maybe things can evolve into being more synapomorphic over time because development is making them more similar because you're now using them together. That goes against the principles of cladistics. It just goes, I think, along with the way biology actually works. Okay, so on that we're going to end. Okay.